Welcome to the e-learning course 1, Portfolio Theory. In lesson 1, you will learn the essential tools for estimating expected returns and risks from historical records and how to consider its implication for future investments. Now let's start with session 1.1, interest rates, risks and risk premiums. The learning goals for this session are: you should be able to differentiate between real and nominal interest rates. You know how to compute and compare returns for different holding periods. And the concept of risk and risk premiums is well understood. Importance of interest rates. The level of interest rate is perhaps the most important macroeconomic factor to consider in one's investment analysis. Forecasts of interest rates directly determine expected returns in the fixed income market as well as in the stock market. Therefore, a superior technique to forecast interest rates would be of immense value to an investor attempting to determine the best asset allocation for his or her portfolio. Now, unfortunately, forecasting interest rates is one of the most difficult parts of applied macroeconomics. But we do have a good understanding of the fundamental factors that determine the level of interest rates, such as the supply of funds from savers, primarily households, then the demand for funds mainly from businesses for commercial loans and some privates for mortgage loans. And then we have the government's net demand for funds, so government bonds on the demand side and as investors on the supply side. And as fourth element, we have the expected rate of inflation, which is impacting the level of interest rates. Real and nominal rates of interest. This is a very important concept to understand. So we need to know the difference between real and nominal rates of interest. The nominal interest rate tells you how much your money has grown, whereas the real interest rate tells you how much more or less of a given good you can buy, also called the purchasing power. So now let's have a look at an example. Now let's assume you have a t equals 0 on your bank account 1,000 Swiss francs. And one bread costs today 1 Swiss franc. So that means with your current amount of 1,000 Swiss francs you can buy 1,000 breads. Now assume the nominal interest rate on your bank account is 10%. So that means 1 year from now your 1,000 Swiss francs is worth 1,100 Swiss francs. Now, as there is also inflation of about 6%, the price of your bread also increases to 1.06 per bread. Now assume how many breads can you buy at t equal 1. So you have 1,100 on your bank account. One bread costs about 1.06, so that results in about 1,038 breads. Now, as a next step, you compare the 1,038 divided by 1,000, so that means you could buy 1.38 breads compared to one bread initially, which is equal to 3.8% real interest rate or purchasing power. The Consumer Price Index. Instead of only comparing by how much the price of a bread changed, a predefined basket of goods and services is used for a family of 4 people. By averaging all prices of goods and services included in the basket, it is a good measure of purchasing power by comparing average prices over different time periods. This is also called the Consumer Price Index or the CPI. Inflation can also be determined by the percentage change in the CPI. As a next step, let's determine the equilibrium of real rate of interest. So to determine the equilibrium of real rate of interest, we use a graph displaying the supply and demand of funds. Now the figure shows a downward sloping demand curve and an upward sloping supply curve. On the horizontal axis, we measure the quantity of funds, and on the vertical axis, we measure the real rate of interest. The equilibrium of real rate of interest is found at the intersection of the demand and supply curve. The supply curve slopes up from left to right because the higher real rate interest rate, the greater the supply of household savings. On the other hand, the demand curve slopes down from left to right because the lower the real interest rate, the more businesses will want to invest in physical assets. As the demand curve is increasing and shifting to the right, the new equilibrium E results in a higher real rate of interest. Continuing on the previous slide, let's do a few examples. With the help of these graphs, you should be able to predict what happens to real interest rates if demand or supply change in either directions. So in the first scenario, fund demand increases because businesses are optimistic and increase their investment activity. As a consequence, the demand curve shifts to the right, resulting in a new equilibrium at a higher real rate of interest level. In the second scenario, fund demand decreases because businesses are pessimistic and decrease their investment activity. As a consequence, the demand curve shifts to the left, resulting in a new equilibrium at a lower real rate of interest level. In the third scenario, fund supply increases because of the Fed's expansionary monetary policy. The supply curve shifts to the right, resulting in a new equilibrium at a lower real rate of interest level. And now, in the last scenario, fund supply decreases because of the Fed's contractionary monetary policy. So the supply curve shifts to the left, resulting in a new equilibrium at a higher real rate of interest level. As you now see, the real rate can be affected by governmental and monetary policies. So far we have learned how inflation can be measured by the Consumer Price Index and how the real rate of interest depends on demand and supply of funds. In the next step, we can compute the nominal interest rate with the help of the Fisher equation. This one describes the relation between nominal interest rates, real interest rates, and inflation rate. The exact Fisher equation shows the calculation of nominal interest rate by compounding the real interest rate and inflation rate. As an approximation, the second formula can be used by simply adding the real interest rate and inflation. Let's have a look at an example using the Fisher equation. If the nominal interest rate of a one-year certificate of deposit is 8% and you expect inflation to be 5% over the coming year, now calculate the real rate of interest first with the approximation and then afterwards with the compounded formula. So now the initial formula is actually the real nominal rate is equal to the real rate plus inflation. So now solve for the real rate. Using the approximation formula, the real rate is simply calculated by using the 8% of nominal interest minus the 5% inflation rate, resulting in 3% real rate of interest. Now for the next question, we actually need to calculate the continuously compounded formula. We start from the basic formula, which is actually 1 plus the nominal interest rate is equal to 1 plus the real rate of interest times 1 plus the inflation. Solve this equation also for the real rate of interest. The solution by compounding is simply 1 plus the nominal interest rate of 8% divided by 1 plus the inflation rate of 5% minus 1. This results in 2.86%. Now, by comparing the approximation result with the compounding result, you see there is a difference of 14 basis points. Taxes and the real rate of interest. For tax liabilities, it's important to understand the impact on the net after-tax real return in an inflation-protected tax system versus a non-inflation protected tax system. The formula below shows how to calculate the real after-tax rate in a non-inflation protected tax system. In the next formula, you can simply substitute the nominal rate with the real rate plus inflation. As the next step, multiply the brackets. So you will get the real rate minus the real rate times tax plus inflation minus inflation times tax minus inflation. So if you actually take the real rate, you get the real rate times 1 minus tax minus the inflation times the tax, and the inflation plus or minus will cancel out. This results in the formula as shown on this slide. The best way to understand the difference between the tax systems is to do a tax example. In an inflation-protected tax system, the tax liability is only due on the real interest rate. In a non-inflation protected tax system, the tax liability is due on the real interest rate and on the inflation. So in this example, we have a 30% tax bracket and your investment provides a nominal rate of return of 12% with an inflation of 8%. So now let's calculate the after-tax real return in an inflation-protected tax system and compare it with the after-tax real return in a non-inflation protected tax system. The after-tax real return in an inflation-protected tax system is calculated as follows. First, calculate the real rate of return simply by using the nominal return minus the inflation return, is equal 4%, and then subtract actually the tax. So what you're going to be left is the 4% real rate times 1 minus the tax rate, equaling 2.8%. The after-tax in a non-inflation protected tax system is actually multiplying the nominal rate of interest of 12% times 1 minus tax minus the inflation rate of 8%, resulting in 0.4% of real return. Now, if you compare the inflation-protected tax system with the non-inflation-protected tax system, you see there is a difference of 2.4%. The incremental tax liability is therefore the inflation times the tax bracket. Excess returns and risk premiums. As different investments have different risks, we introduce a risk premium. The risk premium is defined as the difference between the expected return of an underlying asset minus the risk-free rate. The risk-free rate is the rate you would earn on assets which are not expected to default, such as T-bills and money market funds. Assuming that governments providing these risk-free assets cannot default. Excess returns are the difference between the actual rate of return on a risky asset and the actual risk-free rate in any particular period. The best way to understand the risk premium is by doing an example. If you have a risk-free rate of 4% per year and an expected index fund return of 9.76% per year, what will be the risk premium? You actually simply compute the index fund return minus the risk-free rate, resulting in an excess return of 5.76%. This means that an investor in an index fund is paid an additional 5.76% compared to a risk-free investment. This is the expected excess return for taking the additional risk. Risk aversion. The expected risk premium of 5.76% for an investment in an index fund, as calculated in the previous example, may be enough compensation for an investor to commit, depending on his risk aversion. An investor with high risk aversion would demand a higher risk premium, and an investor with a lower risk aversion would actually demand a lower expected risk premium. Risk-averse investors always require a positive risk premium, otherwise they wouldn't invest. By now we are at the end of session 1.1. After having carefully studied the slides and relevant chapters in the book, please start with the review questions.